3.5, conditional probability and independent events. Conditional probability of event E given event F is written like this. So this word given is going to be this symbol right there, E given F. And you've got an equation for that. Probability of E given F equals the probability of E and F, or that means both, over the probability of F. So kind of look for the pattern there. This second one is the one that's on the bottom. That's kind of what's important to notice. Example 1 is a simple example of the formula. Probability of E is 0.4, probability of F is 0.5, probability E and F is 0.2, find probability of E given F. So I would just kind of write down the formula again. E given F equals E and F over the second one. Okay. So there's some information that I don't really need. I don't really need this, but E given F is 0.2. Probability of F is 0.5. And so we can divide that or just multiply by 10. You can see the fraction is going to be 2/5. Example 2, they changed the letters, but it's still the same thing. The formula for A and B, probability of A given B equals the probability of A and B over probability of the second one. This time it's a little bit different because they give me different information. They're giving me probability of A given B is 0.5 and probability of B is 0.7, but we're missing this information. This is what we want. So if you wanted to rewrite, basically it looks like that. So we can cross multiply. X is going to equal 0.5 times 0.7, which is 0.35. 0.35. So probability of A and B is 0.35. All I'm doing is using that formula there. Skipped example 3, going straight to example 4. At a local college, 4/5 of students live in a dorm. Of those who live in a dorm, 1/4 have a car. Find the probability that a student lives in a dorm and has a car. All right, so a couple of things. It says, I would probably rewrite and take it out of a story problem and write it more like what the equation looks like. So probability that a student lives in a dorm is 4/5. Now the second sentence is the tricky one, I think. Of those who live in a dorm, 1/4 have a car. What you need to think about is the word given. All right, given implies that one of those things happens first. And so you think about what comes first in that sentence, living in a dorm or having a car. And I think living in a dorm happens first. So that's the given part. The given part is the part that happens first. So the way I can read this is the probability of having a car given that they live in a dorm is 1/4. And then the question part says find the probability that a student lives in a dorm and has a car. All right, so I'm going to call that probability of C and D. Okay, D and C, either way, doesn't really matter. It's the same thing. Dorm and car, car and dorm, same thing. And that's what we're trying to find. So you've got the exact same pieces of information that we need for that formula. Probability of C given D equals probability of C and D over the probability of the second one, like that. So this is like the last one. We've got this number over here is 1/4, and we've got this number down here is 4/5, and we're trying to find the and. We're trying to find both. So we can kind of go over here and say 1/4. Feel free to change them into decimals if you want. And so, I don't know, people struggle with this, but really it's just, you can set it up like a proportion and cross multiply. X is going to equal 1/4 times 4/5. It's probably easier to not change it into decimals. Those fours cancel, I'm left with 1/5. So there's your probability. The probability of living in a dorm and has a car is 1/5. Number 5, a class contains 40% women and 60% men. There's a 25% chance of selecting a business major given a woman is chosen. Okay, so that's kind of an important word. Find the probability that a student chosen from the class at random is a female business major. All right, so let's go back and look at what they have. 40% women, so probability of, they use woman here and they use female here, so pick one, either W or F. I'm going to pick F for female. Probability of female is 0.4, and probability of male is 0.6. 25% chance of selecting a business major given a woman is chosen. All right, so that use that word given and use the context of the sentence to figure out which one happens first. Which one happens first, business major or woman? Okay, and so, you know, this is what happens first. That's the given part. So probability that it's a business major given that it's female is 0.25. That's tough. And so find the probability that the student chosen from the class at random is a female business major. You could put the word and right here, female and business major. That's what we're trying to find. And again, if you switch those two around, it doesn't matter. But you can't switch the given around. The given, the female happens first, so that has to be in that second position. But that's what we're trying to find here, is the and. And so again, it's just the same. It's the same equation. Probability of B given F equals the probability of B and F over the probability of the second one. So B given F, 0.25. Probability of F is 0.4. And we're trying to find the probability of B and F. 0.25 equals X times 0.4. You're going to end up cross multiplying that. You don't really need to think of it as a proportion, but that's, you know, people, maybe if that makes you feel comfortable, I guess. 0.25 times 0.4 is 0.1. So there's your probability of B and F. Probability of a female business major is 0.1. 6, numbers 5, 6, 7, 8, and 9 are written on slips of paper. 2 slips are drawn at random, one at a time without replacement. Find the probability that the first number is 6, given that the sum is 15. Okay, so, you know, you got a piece of paper with a 5 on it, a piece of paper with a 6 on it, a piece of paper with a 7 on it, and so on. That's what they mean by that. 2 of them are drawn at random. Find the probability that the first number is 6, given that the sum is 15. So we're trying to find probability that the first one is a 6, given that the sum is 15. So we can use our formula, probability that the first is 6 and the sum is 15 over probability that the sum is 15. Now this one seems harder because they don't really give me the numbers, but let's look at the sample space. Let's look at everything that could be possible. You're picking out 2 of these slips of paper. So I'm just going to list out the sample space. Maybe you get a 5 and a 6, a 5 and a 7, a 5 and an 8, a 5 and a 9. Or you pick a 6 first and you get 6, 5, 6, 7, 6, 8, 6, 9. Okay, or you pick a 7 first, 7, 5, 7, 6. Notice you can't get 7, 7. You can't get doubles because you already picked that number out. 8, 5, 8, 6, 8, 7, 8, 9, or 9, 5, 9, 6, 9, 7, 9, 8. Those are the only possible things that could happen. That's basically the sample space. I see what, 20 different possibilities there. Okay. So look at getting the sum of 15. Okay, let's do that first. So sum of 15 is like this one, and this one. Are there any other ways to get a sum of 15? Yeah, this one. I see 4 of them. 4 of them out of 20. So this probability of sum of 15 is 4 out of 20. Now think about it. The first number is 6 and the sum is 15. It's this one. That's the only way to get the first number 6 and a sum of 15. So that's 1 out of 20. So if we want to find this answer, we need to divide those two fractions. 1/20th divided by 4/20ths equals 1/4. And that's the answer. All right. Now, an easier way of doing this is just look at the green. The one we want is 1 out of the 4 ones that I underline. It's just 1 out of 4. So we can kind of skip over that first step if we want. Part B, find the probability that the first number is 5 given the sum is 13. So probability that the first one is 5 given the sum is 13. That's the probability that the first is 5 and the sum is 13 over the probability that the sum is 13. So check it out. Sum is 13. There's one, there's one, there's one, and there's one. So again, there's only 4 of them. And the first one is 5. This is going to be 1 out of 4 again. All right, 1 out of 4. It's the same. It's basically the same problem. Independent events. One event occurring doesn't affect the probability of another. If you flip a coin and the probability is 0.5 that you get tails, you flip that coin again, okay, it doesn't matter that you got tails. Sometimes people think, well, I flipped a coin 5 times and it was tails every time. It's got to be heads this time. But that's not how probability works. It's still, even if you flipped tails 10 times in a row, the probability that that next one is tails is still going to be 0.5. The previous flips should not affect the next one. So that's independent. Whatever already happened doesn't affect the probability of something in the future. Okay. So events E and F are independent if and only if this. Okay. So this is a good test. This equation is a good test for if they are independent. Number 7 says events A and B are independent with find probability of A and B, and probability of A or B. Okay, so since we know that they are independent, then that means we get to use this equation. You don't get to use that equation unless they're independent. So we can find the probability of A and B pretty quickly because we know it's just going to multiply these two probabilities. Probability of A is 0.2, probability of B is 0.5, or 0.15, sorry. So if we multiply those two numbers, 0.2 times 0.15 is 0.03. Probability of A and B is 0.03. Now we need to find the probability of the union. And this is going to be hard for some of you, but you have to remember a formula from a previous lesson. We know the union rule, and this always applies. A double is going to equal a single plus the other single minus the opposite double. And so since we just found the intersection was 0.03, then all we really need to do is say 0.2 plus 0.15 minus 0.03. So that's going to be 35 minus 3 is 32. That's 0.32. the probability of the union is 0.32. So make sure, if you've got a formula, it's going to still apply. Something from the previous section is still going to apply in this section. Number 8, probability A is 0.5, probability of the union is 0.9. Find probability B if A and B are mutually exclusive. Okay, well, mutually exclusive, let's draw a picture of that. When they say mutually exclusive, they mean that there's no overlap. And so your Venn diagram would look like this. And probability of A is 0.5. And it says probability of A or B is 0.9. And so you can subtract and figure out that that's got to be 0.4 right there, right? Because A or B is 0.9. There's no overlap to worry about. So it's just you add those things together. You know, if you think about it as the union rule, 0.5 plus 0.4 minus 0 overlap. There's your 0.9. And so probability of B in this case is 0.4. Now, if A and B are independent, okay, if A and B are independent, then we've got that formula that we just talked about. Probability of A and B equals probability of A times probability of B. Now, don't use part A. That was a different thing. All right. So forget about that number from before. We're starting over basically, right? And so we know A is 0.5. Probability of A is 0.5, but we're missing two things in our equation for this. But notice they give us this. And so usually we can use the union rule to figure something out here. All right. So let's look at the union rule. Probability of the union equals probability of the single plus the probability of the other single minus the probability of the other double. Okay. So again, we know that probability of A is 0.5. We know the probability of the union is 0.9, but we seem to be missing some stuff. And so what we're going to do here, and this is kind of tricky, but we're just going to call this X. Probability of B is X. And so when I know that they're independent, I'm going to plug this in right here. And we called that X, right? Probability of B was X. So I'm going to replace this with 0.5X. It's a weird thing to do, but the result is I've got an equation with only one variable I should be able to solve. So let's subtract this over and get 0.4. And let's combine our like terms. 1x minus 0.5x is 0.5x. And I can divide by 0.5. That's going to be what? 4/5. 4/5, right? That's 4/5. X is 4/5. So that's my answer. That's that's what I wanted. I wanted probability of B. I'll let probability of B equal X. Probability of B is 4/5, or 0.8 if you want the decimal. Number 9, determinative events A and B are independent. So, you know, it's really the same. It's the same equation. Probability of A and B equals probability of A times probability of B. If they say the word independent, you're probably going to use that equation right there. So it says 2 dice are rolled. A, the first roll is a 1. B, the sum of the dice is 8. Okay, so the sum of the dice is 8. Let's go back to here. Okay, and remember this picture. So the first one is a 1. The first one is a 1. There were 6 things. So the probability that the first one is a 1 is 6 out of 36. Now the other one, the sum is an 8. The sum is 8 is these 1, 2, 3, 4, 5. There are 5 of them. So probability that the sum is 8 is 5 out of 36. Okay. So probability of A is 1/6. Probability of B is 5 out of 36. Right? Because that was 6 out of 36. So that's 1/6. And so according to our formula, probability of A and B equals probability of A times probability of B. So probability of A is 1/6. Probability of B is 5/36. Okay. So we can calculate the probability of A and B, but we can also just look at that chart. The probability of both of those things happening. The first one is a 1 and the sum is 8. Well, you look at it, the first one is 1 and the sum is 8 doesn't happen. The probability of both of those things happening is going to be 0. And so we know the probability of this is 0 according to our sample space. And so we can tell, I don't need to multiply that out, we can tell that that's not true. This equation is false. And so we can answer the question, are those two independent? A and B are not independent. So then the next one, we got a box contains 7 green marbles and 3 blue marbles. You randomly draw 2 marbles, one after another, without replacement. The first marble is green, the second marble is blue. Okay, so we can kind of tell what's going to happen here. We've got 7 greens, 1, 2, 3, 4, 5, 6, 7, and we've got 3 blue ones, blue, blue, blue. Okay. I pull out it says the first marble is green. So probability of A is 1, 2, 3, 4, 5, 6, 7 out of 10, right? 7 out of 10. Now, the probability of B, so we already took out a marble. So you don't know which one it is. It's a 70% probability that you pulled out a green one, but you don't necessarily know. The probability of blue depends on what happened first. Because if I pulled out a green one, the probability of blue would be 3 out of 9. But if I had pulled out a blue one the first time, the probability would be 2 out of 9. And so in this case, the probability of the second one depends on whatever happened the first time. This is not independent. I don't need a formula to tell me that.
10. A bicycle factory runs 2 assembly lines, A and B. 95% of line A's and 88% of line B's bikes pass inspection. 30% of all bikes come from line B. Find the probability that a bike did not pass inspection and came from line B. I think this is a really tricky question. I'm pretty sure there's a homework question that's exactly like this, all right? So look alive here. When I go back through here, you have to read it really carefully. But it says, okay, 95% of line A's bikes pass inspection. Okay. And so the way I read this is as a conditional. I see the probability that it passes given that it was on line A equals 0.95. Similarly, I see 88% of line B passes inspection. And so I look at it as the probability that it passes given that we knew it was on line B is 0.88. So what do we have here? 30% of all bikes come from line B, so the probability of B is 0.3. And then they ask me for probability that a bike did not pass inspection and came from line B. So they want to know the probability that it did not pass. So notice I use the complement and from line B. Okay, so this was really tricky for me because they've got a couple of different things going on. We know it's a conditional problem because we've got that given that symbol. But we've also got the negation. We've got the complement. Okay, so I can try to use my conditional formula. And I want to use these two pieces of information. So let's use the probability that it did not pass, given that it was on line B, equals the probability that it did not pass and on line B over the probability of the second part of the conditional, probability B. Okay, I'm going to use that formula right there. So one problem is we don't necessarily have this information, although it's pretty easy to figure out. Because we look right here, the probability that it passes, given it's in line B, is 0.88. It's pretty easy to figure out the probability that it does not pass, given that it's on line B. Anybody tell me what that number must be? Let me 0.12, that's right. Because we know the probabilities have to add up to 1. Probability that it passes on line B is 0.88. So the probability that it did not pass from line B is 0.12. So I can fill in that number. And I see the probability of B is 0.3. So really, I can just fill in those numbers. This number was 0.12. I'm trying to find the probability of not pass and line B. And this number, probability of B, was 0.3. So let's multiply. Probability that it does not pass and on line B equals 0.12 times 0.3, which is 0.036.